Hello class, welcome to Geometry Lesson 11.4, Spheres. So our essential question today is, how does the volume of a sphere relate to the volumes of other solids? We also want to calculate the volume of a sphere and solve problems involving the volume of spheres. We also want to address the question, how can the surface area of a sphere be calculated? And that's going to be one of our goals as well, is to be able to calculate surface area as well as volume. All right, so let's talk about the volume of a sphere. So here we have a hemisphere, which is half of a sphere, and we have a cylinder on the right hand side, and in the cylinder we have a cone that is cut out. So this is a cylinder and a cone put together. So this cylinder has a cone cut out in it. So first off, what we're going to do is we're going to slice this plane, slice each of these solids sort of like in half. It doesn't have to be at the halfway point, just somewhere that is not the base of the shape. And if we slice this with a plane, then you can see that we have these cross sections here, which are both circles. And we want to figure out the area of these cross sections. You can see the one on the right is a smaller circle because you're looking at the cone part inside the cylinder, right? Because it's not a full cylinder anymore. It's a cylinder with a cone inside. So we're only looking at that intersection there with the cone. And so if we were to slice this, we have the circle on the left, which is a larger circle, and let's go ahead and label some of these dimensions. So let's assume that this hemisphere is of radius r, as given in the diagram, which means that the height of this cylinder is also going to be r, so that's given here. And let's assume that the plane that cuts the hemisphere is at a height h. Let's say the radius is 10, then the h could be something like 4 centimeters or whatever. And so that height is going to be the same for the cone as well, the cone-cylinder combo. Now, in order to get since we know that the height is h and the radius is r, then by Pythagorean theorem, we can get this radius of this circle inside right here, this circular cross-section, by using the Pythagorean theorem, r squared minus h squared is equal to this one. And so that's how we get the radius of this circular cross-section. Now the one on the right, this smaller circle, in order to get the area of this small circle here, I need to take the radius of this larger circle, which is r, because that's the radius of the cylinder, and I need to subtract that by the radius of the smaller circle, which is here, which is this h. And I know that's h because if the radius, so the radius of this cylinder is actually equal to its height. So if you look at that, the radius is equal to the height. And so that means that if this is h, then that has to be h. If this is the radius, then this has to also be the radius. So they're all equal to each other. And so therefore the radius of the smaller circle is h. And so the area of this circular cross-section on the left for the hemisphere is pi r squared, and the r, the radius, is this new radius for that, which is given by Pythagorean theorem. And so that's my r, my new r, and it's squared. And so notice that the square and the square root cancel, leaving me with pi times r squared minus h squared. And that's the area of that cross-section. Now the one area of the cross-section on the right, well, it's going to involve this smaller circle and this larger circle here and the smaller circle inside, right? So in order to get the space in between, right, that's what we want, is the space in between, because it's between the cone and the cylinder. Then we have to take the difference in the area. So we got to take the difference of the larger circle and then the smaller circle, and therefore we get the same exact thing. So notice that the areas of both cross sections are the same formulas here. And therefore, by Cavaliere's principle, if the cross-sectional areas are the same, then that must mean that, and if the heights are the same, then that must mean that the volumes are the same. So that means that the volumes of both of these are the same. So these have the same volume. So volume is the same for both. And therefore, we can use this formula to help us out. Okay, so now taking a look at this again, since this is the volume of a hemisphere, right? This is a hemisphere. We need to figure out the volume of that. That's what we're trying to figure out, is what is the volume of a sphere or hemisphere. Now, in order to do that, we know that it has to equal the volume of the cylinder minus the cone. So if we take the formulas for the cylinder and then minus it from the formula from the cone, we get the volume of our hemisphere. So the volume of the hemisphere is the volume of the cylinder minus the volume of the cone. And so the volume of the hemisphere, which is the cylinder minus cone, well, we know that the cylinder, the height of the cylinder is equal to its radius, right? So this is h, which is equal to r. And we know that the radius of the cylinder is r. And so the formula for the cylinder is pi r squared h. And so we can plug in h for r, and so that gives us pi r cubed, essentially. Same deal for the cone. The cone here, the radius is equal to its height. So this is this h is equal to r, and is equal to r for that cone, right? And so if we plug that in, we get pi r cubed minus 1/3 pi r cubed. And so therefore, we can say that the volume of the hemisphere must be, this is the same thing as 3/3 pi r to the third power, because if this is an invisible 1, we can give it a denominator of 1, and then we can multiply by 3 top and bottom, so that we can get a common denominator. So then that becomes 3/3 minus 1/3 is 2/3. And so we get the volume for our hemisphere, which means that the volume of the sphere has to be double the hemisphere. It's 2 hemispheres to make our sphere right here. And so therefore, our formula for the volume of the sphere is 4/3 pi r cubed. And those are my 2 formulas for the hemisphere and the sphere. So hopefully that made sense. We kind of went through that a little quickly, but that's just, you know, a way to kind of derive the formula. There's other ways to do it as well. So for example 1, we have 2 solids and we want to figure out the volume. So for the first one, we have a sphere of radius 5. So we can go ahead and plug it in. Now we know the volume for the sphere is 4/3 pi r to the third, so 5 to the third. And we got 4/3 pi times, now we got 5 to the third, and 5 to the third is 125. So we got 125, and then we can do, so in order to multiply, you multiply 125 times 4. So 125 times 4 is 500, so you get 500 pi over 3. And there's my volume for my solid, for my sphere. And you could do 500 divided by 3 if you want. You'll get a decimal, and then you can write it as 166.7 pi. But I'm just going to leave it like that. And you can replace pi with 3.14 and get a number as well. Now for part B, we have a semi or a hemisphere. So that means it's going to be 2/3. It's going to be pi and then times the radius cubed, right? And the radius here is pi. That's my radius. So we have pi to the third. So this just becomes 2/3 pi to the fourth. 2/3 pi to the fourth power, because we got third power here and then 1 power here, total of 4. And then of course that's our volume, and then you can replace pi with 3.14, raise it to the fourth power, multiply by 2, divide by 3. We'll go ahead and get that just for this problem. So we'll actually use pi on the calculator, and we'll raise that to the fourth power and times it by 2, then divide by 3, and you get roughly 64.9 for the volume. All right, so let's talk about the surface area of a sphere. Now, in order to do the surface area, what we're going to do is we're going to take a sphere with radius r, and we're going to enclose it so that it's perfectly tight with a cylinder of radius r. And the cylinder has to have a height of 2r, right? It has to have a height of 2 radii stacked upon each other in order to equal the height of the sphere, right? So this is a perfect tight fit for this sphere. Now, the reason why we do this is because we know the area of a cylinder. We know the surface area of a cylinder. It's these 2 circles here, and then the part that wraps around, right? So we're interested in the part that wraps around. We're not interested in the top, the lid, and the bottom. We're just interested in the surface area around the cylinder. And so we can unravel the round part of the cylinder, right? The part that wraps around, and that's just going to be a rectangle. And since the rectangle has to wrap around the cylinder, right, the label of the cylinder, let's say a label of, baked beans or something like that, this paper label has to wrap around the cylinder, so it has to wrap around the circumference, and circumference is 2 pi r for a circle. And the height of this particular label is 2r, right, 2 radii. And so the area, or the lateral surface area for the cylinder, is 2 pi r times 2r, which is 4 pi r squared. So there's my lateral surface area. Okay, so now we got this area, and we want to see if this matches that of the cylinder. Okay, so I'm going to try to do the best I can to kind of convince you just with a graphic. It's going to be kind of approximate to kind of show you, give you an idea of, well, how can I wrap this around the sphere? Okay, so let's say we take that rectangular piece of paper with an area of 4 pi r squared, and let's cut it around the edges. So let's cut it and make round cuts in the left and the right, and we'll cut that off just for now, and then we'll include those back in the sphere in the calculation later. So then we take that round, looks like an oval shape kind of, and then we wrap it around the sphere. So let's go ahead and put the sphere there in the middle, and then we'll wrap it around. If we wrap it around, it's going to look kind of like this. So hopefully you can kind of see that. Again, this is an approximation to kind of give you an idea. And then now let's include those other pieces that I cut earlier, and then we'll try to include them in the top. So we'll put them on the top there, and then we'll kind of fold them in, because remember, this is a three-dimensional object, so you have the top part that's wrapping around into the top of the sphere, and that wraps around, and we get the surface area of the sphere. So this wraps around the entire sphere. Hopefully you can kind of see that. It's kind of hard to visualize, but it's the best there to kind of show you. And so there you go. So that means that the area of that rectangular piece, remember, was 2 pi r times 2r, which was a total of 4 pi r squared. And since it covers the entire sphere, that must be the surface area of the sphere, and therefore that is our formula. All right, so now we got the surface area of a sphere. Let's explore one more thing. We can also think of if we were to cover this entire sphere with aluminum foil or some kind of, paper, we can actually take that paper and peel it off the sphere, and in turn actually fill it 4 circles of radius r. Now this radius r is based on this great circle. This circle that you see here is called the great circle, which is the largest circle in a sphere, right? Which is that sort of like the equator of planet Earth, right? Is that largest circle. If I were to take that and trace it into these 4 circles, then in order to peel all of the peel this onion, I guess, this outer layer of this the sphere, then it would fill 4 circles. And remember that the area of a circle is pi r squared, and so therefore the surface area of the sphere is 4 pi r squared. So now we know another way that you can think about it. You can think about it as it fills 4 circles, and therefore it's 4 pi r squared if you were to peel the outer layer. All right, so now if we were to think of it like that, then if I had a hemisphere, this is an open hemisphere, by the way. An open hemisphere is just literally half of that sphere, but the inside is hollow, right? So, or rather, this part is open. So there's nothing. It's not solid or anything like that. And so I guess you can kind of think of it as a hollow hemisphere, and therefore it would fill 2 circles, right, as opposed to 4. And so then the area has to be, for the open hemisphere, 2 pi r squared. Now, if we had a closed hemisphere, something like this, where it's actually solid here, right? This area is solid material, then that would change things a little bit, because now the dome part is 2 circles worth. This dome part is 2 circles, and the top surface there is 1 circle, right, of radius r. Remember that the radius of this is the same there. And so, therefore, it would fill 3 circles, 2 for the dome, and 1 for the top surface there. And so, therefore, the surface area of a closed hemisphere must be 3 pi r squared. All right, so now we got the formulas for volume and surface area. Let's go ahead and calculate the surface area of the solids here. We have a solid sphere with a radius of 13. So all you got to do, surface area of a sphere is 4 pi r squared. And so the radius has to be 13. So 4 pi times 13 squared. And so we'll multiply that. 13 squared is 169. And then we can multiply that by 4. So we get that the surface area is 676 pi. And there you go. You can compute that as a decimal if you like. And then the surface area of this hemisphere. Now this is, they don't really tell you if it's solid or not. So we're going to assume that it's, well, we're actually going to calculate both. So we'll calculate if it was open, and then we'll calculate if it was closed so that you can get some practice. Usually they'll kind of tell you, or you'll kind of get it from the context. So let's calculate for both. If it's open, then it's 2 pi r squared. So it's 2 pi times 4 squared. And 4 squared is 16. 16 times 2 is 32 pi. And then if it was closed, right, if this was a solid face there, then it would be 3 pi r squared. So 3 pi times 4 squared. And then 16 times 3 is 48. So then in that case, it would be 48 pi. So you got two potential solutions depending on the solid. All right, so let's finish up with the final example. We have two hemispheres put together, one on top, one on bottom, and then we got a cylinder in between. So pretty interesting little shape here. And so since we have two hemispheres, really with the same radii, the radii is the same for both of these, well then that must mean that if I put them together, I get one sphere. Okay, so two hemispheres give me a sphere, right? So basically we just have to do the volume of a sphere. Okay, so and then we do the volume of the cylinder. So let's do the volume. The net volume is the volume of the sphere plus the volume of the cylinder. And so the volume of the sphere is 4/3 pi r cubed. R is 5, so 5 to the third. Plus, and then the cylinder. Remember, the formula for the cylinder is pi r squared h. Now the r is 5. And then the height is 6. And then we'll go ahead and add these together. So we get 5 cubed is 125 times 4. So this is 500 thirds pi plus, and then 5 times 5 is 25. 25 times 6 is 150. So we get 150 pi. And again, we're going to add these, combine these two fractions together. This is over an invisible 1. It needs to have a denominator of 3. So we'll multiply by 3 top and bottom. And so this becomes 450. 450 pi. And so we got 500 over 3 pi plus 450 pi over 3, which is a total of 950 pi over 3. And there's my total volume. Of course, you can get that as a decimal, but I'm just practicing the fraction there. All right, so now the surface area, the net surface area or the total surface area. Now for the surface area, we're doing just the dome, right? The dome part. Now if you're just doing the dome, that's 2 pi r squared, right? And then we got another dome, so that's another 2 pi r squared. So that's a total of 4 pi r squared. So we got 4 pi r squared. And then we have this cylinder, just that outer part of the cylinder, not even the bottom and top of the cylinder, because that's being covered by the sphere, right? The hemispheres. So just the outer part. Now the outer part is 2 pi times the radius times the height. All right, so there's our surface area. So let's go ahead and do it. 4 pi times 5 squared plus 2 pi times 5 times 6. And so we got 25 times 4 is 100 pi. We got 5 times 6 is 30, times 2 is 60, so 100 pi plus 60 pi for a total of 160 pi. And there's my net surface area for the solid. All right, that's going to do it for the video, guys. I hope you found this useful. I hope you found this informative. You learned a few things. As usual, I'll see you in the next one.